will simply give you some facts. And so I will accept the fact that the cloud is going to be charged. This is the cloud. Positive at the top, negative at the bottom, and here is the Earth. Because of induction, the Earth, of course, will therefore become positively charged here. And so we're going to see field lines, electric field lines, which go from the Earth to the cloud, always perpendicular to the equipotentials. Something like this. I'll give you some dimensions. This may be something like 5 kilometers. This vertical distance, d, is about 1 kilometer. These are typical numbers, of course. It can vary enormously from thunderstorm to thunderstorm. And this height is something typically like 10 kilometers. And this allows us now to make some very interesting calculations, to get some feeling for the potential difference between the cloud and the Earth. That's the first thing we can do. If we make the simplifying assumption that the electric field is more or less constant here, it's like having two parallel plates where the electric field is constant between them, then the potential difference, delta V, between the bottom of the cloud and the Earth is simply the electric field times the distance d. So this becomes E times d. But if the breakdown occurs at 3 million volts per meter, by the way, that's dry air. When there's a thunderstorm, it's probably not so dry. But let's take the 3 million volts per meter. So we get 3 times 10 to the 6. That is for E. And the distance between the cloud and the Earth, let's take 1 kilometers. So that's 10 to the 3rd meters. So we get of the order of 3 billion volts between the Earth and the clouds. And the values that are typically measured are several hundred million to 1 billion volts, so it is not all that different. You expect that the potential is probably less than what we have calculated, because clearly these are not flat surfaces. There are trees here on the ground, there are buildings on the ground, which are like sharp points where the electric field will be locally higher, and so you will get a discharge at these sharp points first, and that means the potential difference between the cloud and the Earth could then be less than the 3 billion that we have calculated here. That's only a back-on-the-envelope calculation. The details of the physics of the discharge are very complicated, but I want to share with you some facts without giving detailed explanations. The start of the lightning begins when electrons begin to flow from the cloud to the Earth. They form a funnel which is about 1 to 10 meters in diameter, and we call that the step leader. The step leader moves about 100 miles per second, and so it comes down in about 5 milliseconds. 5 milliseconds from here to here, and it takes about half a Coulomb to the Earth. Half a Coulomb for about 5 milliseconds, that means the current is about 100 amperes. The step leader creates a channel of ionized air, full of ions and full of electrons, which is an extremely good conductor. And when this step leader reaches the ground, there is this highly conductive channel, and the electrons can now very quickly flow from this channel to the ground. And that starts first right here at the surface of the Earth. That's where the electrons will first go to the Earth, and then successively, electrons which are higher up in the channel will make it down to the Earth. And so you're going to see electrons going through the channel to the Earth, but first the electrons are closer to the Earth, then the electrons farther away, and then even farther away. And this is actually where most of the action occurs. The current is now enormously high, 10,000 to some 100,000 amperes, and you heat the air, you get a tremendous amount of light, the ions recombine, and you get pressure, heat produces pressure, and there comes your thunder. And so most of the action is not in the step leader, but is in this second phenomenon which we call the return stroke, which is from the Earth to the cloud. And the speed of that return stroke is about 10 to 20% of the speed of light. During the return stroke, there is about 5 Coulomb exchange between the cloud and the Earth, and 5 Coulomb is a sizable fraction of the total charge that was on the cloud to start with. After a return stroke, maybe 20 milliseconds later, this whole process can start again. You can get a step leader and you can get the return stroke. However, the step leader will now follow exactly the same path that was made before, because that's where the air is ionized, so that's where the conductivity is very high. So that's the easiest way to go. And this process can recur 5, 10, maybe 15 times. So what appears to you as one lightning bolt, in fact, could be 10 flashes back and forth between the cloud and the Earth. And the real light is not in the step leader, that's very little light, but the real light is in the return strokes. So 10 return strokes, which may be 20, 30, 40 milliseconds apart, appear to you and to me only as one flash, which would take place maybe in as little as a tenth of a second. And during these 5 or 10 return strokes, you exchange between the cloud and the Earth maybe a total of 25 to 50 Coulomb, and that of course will lower the potential difference. And if the potential difference becomes too low, then the process stops. You have to wait now for the cloud to charge up again, and then lightning will strike again. And that can take anywhere from maybe 4, 5, 10, 20 seconds. And then you get another lightning bolt. The study of this process, of the step leader and of the return stroke,